Hello everyone and welcome to chapter 4. So in chapter 4 we're going to be focusing on neighborhood operators. So in the last chapter, chapter 3, we applied operations involving multiplications and summations to map an image, the entire image, into some kind of representation space. Now you may have noticed that in doing that mapping, some of the basis images, for example the Haar basis image, only had non-zero weights or non-zero values in certain subsets of image space. And so these basis images have the useful property that when you map the images into transform space, that certain coefficients in transform space tell you about local information within the region or within the image. So, and those regions could be varied across the image. If you look at the Haar basis images as well, particularly when you look at those where the basis images are zero but localized to a little corner of the image, just have a look at those basis images again and you'll see that they consist of shifted versions of the same pattern applied to the different corners of the image. Now, the natural extension of this is actually to apply local operators to an image to compute some properties that describe structure over a small region of space centered on wherever the basis image happens to be centered. Or more correctly, rather than thinking about a whole basis image, we flip this on its head and we start with a local operator, and that local operator then gets applied at different points across the image. The same operator applied to different neighborhoods. So that's the basic idea of neighborhood operators. They come in two broad classes, linear, and the obvious example of that would be convolution operators. And we'll see that computing local averages over space it represents another example of a linear operation, and that can be represented by the operation of convolution. So we'll use that to actually get an intuition about how convolution works. There are also, however, nonlinear operators, and these are operators which can't be expressed using simple multiplications and additions. You would normally have some other kind of operator, some other sort of mathematical operation being applied, such as sorting, which, so in other words, sorting of intensity values in a neighborhood, and median filtering is one example of that. Morphological operators are also known as shape-based operators. So they rely on applying set theoretic mappings to local regions of the neighborhood or local regions of the image. So one of the interesting things, however, about linear, so we're going to look at both linear and nonlinear, but nonlinear actually represents a huge class, but it is very difficult to get a handle on that class. Linear operators also represent a very large class, but the nice thing about linear operators is that they can all be implemented by convolution. So linear neighborhood operators are strictly all implementable through spatial convolution. The nonlinear neighborhood operators are typically implemented through statistical operations, which include sorting operations, set-based operators, which we'll go on to define when we get to mathematical morphology, and or also applying a nonlinear function to the output of a linear neighborhood function. There's an L there that shouldn't be there. Okay, so we have this thing that we can do to convert linear operator implemented by convolution into something that's nonlinear, and we're going to explore how that's done later on in the lecture, because that forms the basis of convolutional neural networks, which I'm sure many of you will have come across or heard about. Okay, so let's have a look now at convolution. Now I'm going to do a separate discussion about certain aspects of convolution starting from first principles. That's not going to be something that's examinable, but it addresses questions that I get every year in the definition of convolution, understanding the definition of convolution. So let's first of all have a look at this definition for the convolution operation, and this is of course a mathematical definition. Oh wow, my tablet has gone quite funky. Let's get rid of that. Okay, let's try this again. Okay, so I'm going to look at this equation here. So here we've got our input image is represented by f. So this is going to be our input. And we have an output image, g. So the output image g is going to be approximately the same size as the input image. So the input image, if it's got m rows and n columns, then the output is going to have approximately the same number of pixels, same number of rows, same number of columns. I say approximately because you'll see that there's one caveat to this, which has to do with the way that convolution works, or what it represents as an operation. So f is our input, and g is our output. H is going to be the thing that defines the mapping between the input and the output, given that we have a linear operator. So this is known as the convolution mask. So convolution mask. And by changing the values of the convolution mask, we can get different mappings between the input image and the output image. But in all cases, this equation holds for that linear mapping. So let's deconstruct this equation a little bit more. But before I do that, what I'm going to do is to jump to this expression here, or this figure here, to illustrate what's going on in convolution. So we've got our mask here, but actually our convolution mask is going to be a flipped version of this. So this is actually, this illustration is after flipping. Wow, this is really very strange, this mouse. This is after, golly, after. Let's redo this. This is hopeless. So this mask is after flipping. There we go. It's okay now. After, wow, after flipping. So I'll explain this flipping thing in a second. This flipping thing sounds like I'm swearing, but the mask flip is kind of part of the definition of convolution. And there are some implementation things that we need to talk about here. Okay, so this is the mask after it's flipping. What does the mask look like before flipping? So when we flip the mask, what we do is we take it, we take the mask as being on a spatial coordinate system, centered usually on the middle of the mask. And so typically we find that odd size masks are more widely used in image processing than even size masks. So a 3x3 mask, a 5x5 mask, 7x7, but it's quite rare to find 6x6 or 4x4. So let's go with the size of an odd mask. So when we flip, what we do is we take the coordinate system of the mask and we invert it along the axis that represents column direction, and we flip it along the axis that represents row direction. So you're inverting the coordinate systems for rows and columns about the center. Okay, so think carefully about what I've said there and replay it if you need to. Let's have a look at what the mask looked like before flipping. Ugh. Okay, so most bizarre thing I've seen in a long time. Wow, that's weird. Okay, so before flipping the mask, the values would have looked like this: 2, 2, and 2. Unbelievable. Okay. Okay, then 0, 0, and 0. Oh man. Okay, 0, 0, 0. Right, I just bashed my mouse on the... Let's hope that works better. What do you know? It's slightly better. No, I think I've broken it. Okay, so 0, 0, and 0. And then we've got, here we've got 1, 1, 1. Okay, let's redraw this as a 0. There we go. Okay, so that's what the mask will have looked like before, before we do the flip. Okay, so after doing the flip, what's happened here is that, so this is the unflipped mask. Okay, so this is unflipped. And if we like, this is before we flip the mask. Unflipped. Okay, so the this is the convolution mask, and this is after flipping before we start applying it. So what happens when we apply the mask? I'll come back to the flipping later on. Just be assured that in the definition of convolution between an image and a convolution mask, the mask must be flipped. Okay, that is according to the definition of convolution. So after flipping the mask, so the reason that this mask looks like this is that when we flip it, so when we go from here to here, what we've done is flip the rows around the center. So the 1s exchange places with the 2s, and the 0s stay in the middle because they're all on effectively row 0 of the mask coordinate system. And that's row -1, that's row +1. And when we flip this way, because the mask is symmetric about this axis, then we don't notice the flipping in the other direction. Okay, so make sure you understand that. What I've said is absolutely correct, so just make sure you get it. So how does the operation then work? So what we then do is we multiply mask values. So first of all, take the center of the mask, right, after it's flipped, and stick it somewhere in the image. And you need to make sure that this mask sits, the center of this mask sits over every single pixel in the input image. So, and what I've done here is to actually start not from the corner pixels, but actually from a little way in. So that 10 there is where I've positioned my mask first of all, just to show you the calculation. So the calculation simply involves multiplying the mask values by the corresponding pixel values. So you get 10 by 1 plus 10 by 1 plus 10 by 1, plus 0 by 10 plus 0 by 10 plus 0 by 10, plus 2 by 20 plus 2 by 20 plus 2 by 20, which gives you 44, which gives you 150. And so where the mask is centered, you place the value of 150 in the output image. So this is our F. This is our G, our output. And this is our H. Okay? Then you move the mask to the center of the mask to the next pixel along, and you repeat the calculation. And so that gives you a calculation that would be, I think would give you 150 again here because of the structure of this particular input image. Okay, so that would be 150 there. And then you keep on doing that across, moving the mask along, repeating the process of multiplication and summing, and dropping the result into array G. Okay. Now we'll come back to how you handle the case where the center of the mask sits on a corner pixel of the image, in which case some values in the mask will fall outside of the region where the pixel values have a definition. In other words, the mask elements will fall outside of the image elements. So we handle that later on, further on in the lecture. But let's ignore that for the time being. Okay, so let's come back to this here. There's our F, there's our H, there's our G. So to interpret this expression, the first thing you do is you assume, for example, that M is 0 and N is 0. In which case you will be able to see that what I'm doing is here, it's an inner product because I'm summing the product of values in two different arrays. So it's a local inner product. But again, if I set this to 0 and I set this to 0, this becomes f of m dash n dash h of minus m dash minus n dash. So that's how you can understand that the operation of the inner product, where m dash and n dash, that's the thing that these are the coordinates you're summing over. Because you sum over these coordinates, they're going to disappear from the output. And so if I set m equals 0 and n equals 0, what I get is g at 0, 0. So I get one value, and that value will be the dot product between the image and the local and the flipped mask, because of the minus here, but plus here and plus here. Okay, so that should be very intuitive. Once you've got that, and again, this trick of setting that to 0 simplifies it. You can immediately see what's going on with this flipping of the mask. So then these values m and n then become the shifts of the mask relative to the image. Okay, because this is a translation, of something as a function of minus m dash by an amount m, and this is a translation of something as a function of minus n dash by an amount n. So you can see this as a translation. Now, if you're confused about that, the thing to remember to look for is this thing here, which is the idea of just going back to one-dimensional signals. You might remember something like this. Whoa. Right. So f as a function of, let's say you have a time domain signal, you might remember this, t minus tau, which is which is something you find in like one-dimensional convolution. It's a similar kind of thing, right? So your dummy variables here, instead of being tau in the case of one-dimensional convolution, which see my supplementary notes on that just to understand that if you've not met it before, that tau is the shift. Okay, so you can recognize then that m dash n dash and m dash n dash are the dummy variables. You sum over those, and that gives you your g as a function of mn. So looking at the mechanics of convolution should be quite simple. There are lots of animations online you can find about convolution. Beware, because some people, some sources describe convolution as being intrinsically a two-dimensional operation, but actually it's defined in one dimension, between two one-dimensional functions. And I will have a supplementary note that explains why convolution is an important operation to recognize from the point of view of modeling physical systems. So let's come back now to how we make this, how we now set the mask values. So you've probably come across the idea of a running average somewhere, where you basically smooth some kind of time series. So let's say that I decide to look at what the average temperature is over the month of February. What I would do is I would record the temperature every day, but that was probably going to be quite a spiky sort of graph. What I can do is I can smooth that graph by treating that a time series of temperature as a function of day. I can do a running average on that. So basically I can take groups of 3 days, 3 consecutive days, and just find the average temperature and just repeat the consecutive days that I take over this 3-day window. Okay, so you could do a similar thing here. So for example, we can look at set a convolution mask which has a value of 1/9 in every pixel of the mask, and the effect of that is that if this mask had values of 1/9 for all of its pixels, then what I'm doing when I compute the convolution is I'm doing a local average of all the pixels in a 3x3 window centered at this location here when the mask is centered at that location over the image. Then when I move the mask to the next location and repeat that process, again, if all the mask values had, all the mask elements had value of 1/9, I'd be effectively performing a local average over a 3x3 region of the intensities in the image. And that would be the output. So the output would be a smoothed version of image intensities from the original image. Okay, so this is what that looks like. So if we take our leaf on grass image, which we've seen before, and we run a 3x3 sliding averager over it, then this is the result we get. Now look carefully at the relationship between this image and this image, just to understand what effect you get here, what effects you get here. First of all, what you see is that the grass area in particular has become a lot more blurry. And that's because there's a lot of fine texture here. So we have a lot of changes over small spatial scales in this image. And we've suppressed those fluctuations. So the background, which is really fine and textury, looks a lot smoother. We also see a bit of loss of detail within the leaf, but actually if you have a look at some elements of this image on the left hand side, you'll see the leaf looks a little bit rough in terms of intensity. Now that's because of the artifact associated with acquiring the image and then compressing it and storing it on in a lossy fashion onto disk. So actually the smoothing operator cosmetically looks pretty good as far as the leaf goes, the interior of the leaf goes. But there's something else I'd like to draw your attention to, which is the contrast between the leaf and the background, right? So here the leaf looks a bit darker than it does here. And the reason for that is that we have effectively suppressed to some extent spatial or regions of the image that have very fine or very high spatial frequencies. And we have enhanced the regions that are dominated by lower spatial frequencies. So there's a little bit of what we call low-pass filtering within the mapping from here to here, done purely by applying a spatial convolution operation. So if you've encountered Fourier transforms before, and perhaps seen some things about how you do frequency domain filtering, there is an equivalent effect of what we've done between the left-hand side and the right-hand side in terms of spatial frequency response. Basically we've applied what's called a low-pass filter to the image. But we've done that through spatial convolution, not by mapping into Fourier domain, applying a filtering and coming out, which I talked about a bit in chapter 3. So you can get this spatial filtering function without actually having to go into the Fourier domain, simply by doing spatial convolution. Okay. Now, the 3x3 sliding average we've seen here effectively weights each pixel with by the same amount when it computes an output value relative to the input neighborhood. Sometimes one might think that if we want to preserve a little bit more the intensity, so give more importance in doing that averaging operation to pixels that are nearer to the center of the mask, then that would be a sensible thing to do. So in other words, if your goal is not to perform aggressive smoothing, but instead to provide an estimate of the intensity of pixels around that neighborhood, but in a way that respects the central organization of the neighborhood. That is, the pixel in the center is nearest to the center, obviously, and pixels that get further away from the center of the mask, wherever it is in the image. So let's just have a look at that, just to get that clear. So when the mask is let's say centered here, we want to produce an output value in here that respects that is a representation of the intensity centered in the neighborhood, centered around this point, but gives higher importance to the pixel center at that point compared to the intensities around the point. Then it would be sensible to use a mask like this, where you've got a higher weighting here, and you've got lower weightings based on the distance of the pixels away from the central point. And so that gives you a mask that might look like this, which is sometimes referred to as an approximate Gaussian mask. It's a very crude approximation. The 1/16th, you can check, make sure that the sum of all values in the mask is 1, which is similar to what we have with this mask. Okay, sum of all values is also 1. So that's consistent with having an unbiased estimate of the average intensity in a neighborhood. So normalizing the mask by so that its absolute value sum to 1 is a very common thing to do when you're doing smoothing of this sort. Okay, now this, as I said, is a very crude approximation to a two-dimensional Gaussian function. There are many reasons why two-dimensional Gaussian functions are extremely attractive to use as the weighting patterns for convolutional masks. First of all, so this is a slightly theoretical argument, but I'll just run it past you so you've heard it at least. When we make a mask like this, if we look at the interpretation of this mask in the Fourier domain, it turns out that this mask introduces lots of ringing in the Fourier domain, something that's known as Gibbs phenomenon. But for those of you who've met ideal filters in the past, what we get is a sinc function as the frequency domain response, magnitude response for this convolution mask. So it's got a main lobe, and then it's got all these bumps. So those bumps might be not a very nice thing if you want to have tight control of frequencies that you let through, and frequencies that you don't, frequencies that you suppress. A Gaussian, on the other hand, has no bumps in the frequency domain. So, well, it's got one main bump in the frequency domain. So Gaussians are optimal from that respect in that they don't induce any ringing in the frequency domain. In fact, the Fourier transform of a Gaussian in the spatial domain is a Gaussian function in the Fourier domain with an inverse width to whatever it is in the spatial domain. So we'll come back to that later on. So one of the things we can do with filtering with a Gaussian mask is to apply the Gaussian mask once, then take the output of that filtering or smoothing operation and apply the mask to that again, preserve the result, apply the mask again to that result, etc. In which case what you do is you get a cascade or a series of images, each of which represents a blurred version with a Gaussian mask of the original image, but with a wider degree of blurring, or effectively using a fatter Gaussian. So this is known as a Gaussian scale space. And as you progressively move through from fine scales to coarse scales, so in other words, blurring with a small Gaussian to blurring with a large Gaussian, then you can see there's a progressive loss or progressive suppression of information in the background and a progressive enhancement of the big structure in this image, which is the leaf. Now the edges of the leaf lose a bit of information, lose a bit of detail, but you can still see it's a leaf even in this figure, right? It's got the shape of a leaf. So the nice thing about Gaussian scale spaces is that they allow you to tune the degree of blurring. Because you preserve all these different levels of blurring, you can actually select the degree of blurring that best suits something you're trying to achieve. And so we're going to look at that a bit more in the context of chapter 5, and we're also going to look at it in practical use, in the chapter on registration, chapter 7, because the Gaussian scale space is used in both of those contexts. First of all, for something called multi-scale edge detection, and also multi-scale gradient estimation, which is a very important process for image recognition without using deep networks. But a key thing I want to emphasize here is that the way that we're doing this operation is by taking our input image. In fact, let me sketch this out, hoping my pen is going to play ball with me.